Introduction to AES CTR mode. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're diving deep into AES Counter Mode, also known as CTR mode. This is one of the most important modes of operation for block ciphers, and understanding it thoroughly is crucial for anyone working with cryptography in modern systems. AES CTR mode is widely used in secure communications, VPNs, disk encryption, and cloud storage systems because of its unique properties. In this presentation, we will walk through every single aspect of how CTR mode works. We will start by understanding what makes it different from other modes. Then we will explore the mathematical foundations, see how encryption and decryption actually work step by step, and finally examine real-world implementations. By the end of this walkthrough, you will have a complete understanding of CTR mode without any ambiguity. What is AES CTR mode? Let's start by understanding what counter mode actually means. CTR mode is a mode of operation that transforms a block cipher like AES into a stream cipher. This is fundamentally different from modes like CBC or ECB. Instead of encrypting the plaintext directly, CTR mode encrypts a counter value and then XORs the result with the plaintext. The term counter refers to a numeric value that increments for each block of data we encrypt. You can think of it like a sequence number that changes with each block. This counter value is what gets encrypted by AES, not the actual plaintext data. The encrypted counter is then combined with the plaintext using the XOR operation. What makes CTR mode special is that it turns AES into a stream cipher. With other modes, you have to wait for one block to finish encrypting before you can start the next one. But with CTR mode, because we're just encrypting counter values, we can encrypt multiple blocks in parallel. This parallelization is one of the biggest advantages of CTR mode and why it's so popular in high-performance systems. Another critical feature is that CTR mode does not require padding. Traditional block cipher modes require the plaintext to be an exact multiple of the block size, which is usually 128 bits for AES. If your data does not fit perfectly, you need to add padding bytes. However, CTR mode generates a keystream that can be any length, allowing you to use exactly the number of bytes you need. Key components of CTR mode. To fully understand CTR mode, we need to know about its essential components. First is the encryption key itself. Just like any AES encryption, you need a secret key. This could be a 128-bit key, 192-bit key, or 256-bit key depending on your security requirements. The key must be kept secret and secure, as anyone with the key can decrypt your data. The second component is the nonce, which stands for number used once. The nonce is a value that must be unique for every message encrypted with the same key. Think of it as a message ID. It is typically 96 bits long, though the exact size can vary. The nonce does not have to be secret or random, it just has to be unique. Many systems use sequential nonces like 1, 2, 3, or they use random values. The critical rule is never reuse a nonce with the same key. The third component is the counter itself. The counter starts at a specific value, often 0, and increments by 1 for each block. If you are encrypting a large file, the counter keeps incrementing. 0, 1, 2, 3, and so on. The counter is combined with the nonce to create the full counter block that gets encrypted. Finally, we have the AES block cipher function. This is the actual AES encryption algorithm that takes a 128-bit block and a key, and produces a 128-bit encrypted output. In CTR mode, we are encrypting the counter blocks, not the plaintext. The AES function is used in encryption mode only, even for decryption, which is another unique aspect of CTR mode. How the counter block is constructed. The counter block is at the heart of CTR mode, So let's understand exactly how it's built. The counter block is 128 bits long because AES operates on 128-bit blocks regardless of the key size. These 128 bits are divided into two parts, the nonce and the counter value. A typical construction uses the first 96 bits for the nonce and the last 32 bits for the counter. This gives you a 32-bit counter, which means you can encrypt 2 to the power of 32 blocks before the counter wraps around. With 128-bit AES blocks, that's about 64 gigabytes of data. For most messages, this is more than sufficient. Let's look at a concrete example. Suppose your nonce is represented in hexadecimal as beginning with 00 and ending with 01. This is a 96-bit value. For the first block, the counter is 0, so the full counter block is the nonce followed by 32 0 bits. For the second block, the counter becomes 1, so the last 32 bits are beginning with 00 and ending with 01. For the third block, the counter is 2, so the last 32 bits are beginning with 00 and ending with 02, and this pattern continues. The beauty of this construction is that every counter block is unique, provided the nonce is not reused. The nonce guarantees that even if the same message is encrypted multiple times, the counter blocks will differ because the nonce changes. An incrementing counter further ensures that each block within a single message uses a distinct counter block. The encryption process step by step. Now let's walk through the actual encryption process in detail. Imagine you have a plaintext message that you want to encrypt. The message could be any length, let's say 300 bytes. Since AES blocks are 16 bytes, you'll need 19 blocks to encrypt this message. Step 1 is to set up your nonce. You generate or select a unique nonce value. This nonce will be the same for all blocks in this message, but it must be different from nonces used for other messages with the same key. Step 2 is to construct the first counter block. You take your nonce and append a counter value of 0. This gives you a 128-bit counter block. You then encrypt this counter block using AES with your secret key. The result is a 128-bit encrypted counter value, which we call the keystream block. Step 3 is the XOR operation. You take the first 16 bytes of your plaintext and XOR them with the keystream block. The XOR operation combines each bit. If the bits are the same, you get 0. If they are different, you get 1. This produces your first ciphertext block. Step 4 is to increment the counter and repeat. You increase the counter to 1. Construct the next counter block. Then, you encrypt it with AES to get the next keystream block, and XOR it with the next 16 bytes of plaintext. This process continues until you have encrypted all the plaintext. For the last block, if your plaintext doesn't fill a complete 16-byte block, you simply use only the number of keystream bytes you need. If you have 12 bytes of plaintext left, you use 12 bytes of the keystream and discard the rest. This is why CTR mode doesn't need padding. Visual representation of encryption. Let's visualize the encryption flow to make it crystal clear. The diagram on the slide shows how data flows through the CTR mode encryption process. At the top, we start with our nonce plus counter value. This goes into the AES encryption function along with our key. The AES function outputs an encrypted counter block, which is the keystream. This keystream is then combined with the plaintext block using XOR. The result of this XOR operation is the ciphertext block that we send or store. Notice that the plaintext never enters the AES function. This is fundamentally different from modes like CBC where the plaintext is directly encrypted. In CTR mode, AES is used only to generate a keystream, and the actual encryption of the plaintext happens through the XOR operation. This architecture has significant implications. Because the plaintext is not going through AES, and because the counter blocks can be generated independently, you can encrypt multiple blocks simultaneously. If you have multiple CPU cores or a hardware AES accelerator, you can parallelize the encryption process, which makes CTR mode extremely fast. The decryption process. Here's where CTR mode shows one of its most elegant properties. Decryption is identical to encryption. That's right, the exact same process that encrypts data also decrypts it. This happens because of the mathematical properties of the XOR operation. Remember that XOR is its own inverse. If you XOR a value with something, and then XOR the result with the same something, you get back the original value. Mathematically, if A XOR B equals C, then C XOR B equals A. This means that plaintext XOR keystream equals ciphertext, and ciphertext XOR keystream equals plaintext. So to decrypt, you do exactly what you did to encrypt. You take the same nonce that was used during encryption. You construct the same counter blocks by combining the nonce with incrementing counter values. You encrypt these counter blocks with AES using the same key, generating the exact same keystream. Then you XOR the ciphertext with this keystream, and you get back the plaintext. This symmetry is beautiful from an implementation standpoint. You only need to implement the encryption direction of AES, never the decryption direction. In some modes like CBC, you need both AES encryption and AES decryption. But in CTR mode, even decryption only uses AES encryption. This simplifies implementations and allows for optimizations. The practical implication is that your encryption and decryption code can share the same functions. The only difference is whether you are XO ring plaintext with the keystream, or XO ring ciphertext with the keystream. Everything else is identical. Decryption flow diagram. The diagram on this slide shows the decryption process, and you will notice it looks almost identical to the encryption diagram we saw earlier. We start with the same nonce and counter that were used during encryption. These go into AES encryption with the same key. AES produces the same keystream that was generated during encryption. This keystream is then XORed with the ciphertext block instead of the plaintext block. The result is the original plaintext. The critical requirement for decryption is that you must use the exact same nonce and counter values that were used during encryption. This means the nonce must be transmitted or stored along with the ciphertext. It is not a secret, so this is perfectly safe. Many protocols prepend the nonce to the ciphertext, so the first bytes of the encrypted message are the nonce, and the rest is the actual ciphertext. The counter starts at the same initial value and increments in the same way. If encryption started with counter 0 and incremented by 1 for each block, decryption must do exactly the same. As long as the nonce, counter sequence, and key match, decryption will perfectly recover the original plaintext. Parallelization advantage. One of the most significant advantages of CTR mode is its ability to be parallelized. Let's understand why this matters and how it works. In many block cipher modes, such as CBC, each block depends on the previous block. For example, you can't encrypt block 2 until block 1 is finished, and similarly, you can't encrypt block 3 until block 2 is finished, and so on. This creates a sequential dependency chain. CTR mode breaks this dependency. Because we are encrypting counter values, rather than plain text, and because counter values can be generated independently, we can encrypt multiple blocks at the same time. If you know you need to encrypt blocks 1 through 10, you can immediately construct counter blocks for all 10 blocks and encrypt them all simultaneously if you have the hardware resources. In modern CPUs with multiple cores, this is a huge advantage. Core 1 can encrypt counter block 0, Core 2 can encrypt counter block 1, Core 3 can encrypt counter block 2, and Core 4 can encrypt counter block 3, all at the same time. Once all the keystream blocks are generated, XORing them with the plaintext is extremely fast. Hardware accelerators for AES make this even faster. Intel processors have AES-NI instructions that perform AES encryption in hardware. With CTR mode, you can pipeline multiple AES operations through the hardware accelerator simultaneously, achieving throughput that is multiple gigabytes per second. This parallelization applies to both encryption and decryption. Since decryption also just encrypts counter blocks, it can be parallelized in exactly the same way. This is different from CBC mode where encryption must be sequential but decryption can be parallel. Random access property. Another powerful feature of CTR mode is random access. Random access means you can decrypt any part of the ciphertext without having to decrypt everything before it. This is extremely useful in many real-world applications. Consider a large encrypted video file stored on a cloud server. A user wants to skip to the middle of the video, perhaps to the 30-minute mark. With CBC mode, you would have to decrypt all the data from the beginning up to that point because each block depends on the previous block. But with CTR mode, you can jump directly to any position. Here's how it works. To decrypt block number n, you simply construct the counter block for position n. You know the nonce because it's stored with the ciphertext. You know n because it's the block position you want. You combine the nonce with counter value n, encrypt it with AES, and XOR with the ciphertext at position n. Done. You've decrypted that specific block without touching any other blocks. This makes CTR mode ideal for encrypted databases, encrypted file systems, encrypted disk volumes, and streaming media. In a database, you might want to read a specific record without decrypting the entire database. With CTR mode, you can do this efficiently. The random access property also enables efficient updating of encrypted data. If you want to modify a single block in the middle of a file, you can decrypt just that block, modify it, re-encrypt it, and write it back without touching any other blocks. With CBC mode, modifying a block affects all subsequent blocks. The critical importance of nonce uniqueness. Now, let's discuss the most critical security requirement of CTR mode: nonce uniqueness. This is extremely important, and I want to emphasize it multiple times. You must never, ever reuse a nonce with the same key. This is not just a best practice, it is an absolute requirement. Violating this rule completely breaks the security of CTR mode. Let's understand why nonce reuse is catastrophic. Suppose you encrypt two different messages using the same key and the same nonce. When you do this, for the first block of each message, you will generate the same counter block. This means AES will produce the exact same keystream block. If you XOR plaintext 1 with that keystream to get ciphertext 1, and XOR plaintext 2 with the same keystream to get ciphertext 2, then an attacker can simply XOR ciphertext 1 with ciphertext 2. When you XOR ciphertext 1 with ciphertext 2, the keystream cancels out, and you get plaintext 1 XOR plaintext 2. This gives the attacker the XOR of the two plaintexts, which leaks massive amounts of information. If either plaintext is known or guessable, the attacker can recover the other plaintext. Even without knowing either plaintext, statistical analysis of the XO-read plaintexts can reveal information. This isn't theoretical. There have been real-world security breaches caused by nonce reuse in CTR mode. One famous example was the Xbox 360, which reused nonces in its cryptographic system, allowing attackers to extract the encryption keys and run unauthorized software. To prevent nonce reuse, you need a strategy. One approach is to use a counter for the nonce. Start at 1 and increment with each message. Another approach is to use random nonces if your random number generator produces high-quality randomness. Some systems use timestamps, but you must ensure timestamps are always unique even if multiple messages are encrypted in the same millisecond. Whatever strategy you choose, the nonce must be unique for every message encrypted with the same key. Nonce reuse attack visualization. The diagram on this slide illustrates what happens when you reuse a nonce. At the top, we see message 1 being encrypted with a specific nonce. The nonce plus counter goes into AES, produces a keystream, and the keystream is XOR'd with plaintext 1 to produce ciphertext 1. Below that, we see message 2 being encrypted with the same nonce. Because the nonce is the same and the counter starts at the same value, the exact same counter block goes into AES. This produces the exact same keystream. This keystream is XOR'd with plaintext 2 to produce ciphertext 2. The bottom of the diagram shows the attack. An adversary captures both ciphertext 1 and ciphertext 2 and XORs them together. Because both ciphertexts use the same keystream, the keystream cancels out in the XOR, leaving plaintext 1 XOR plaintext 2. This leaks information about both plain texts. If the attacker knows or can guess plaintext 1, they can XOR it with the result to get plaintext 2. Even without knowing either plaintext, patterns in the XOR reveal information. For example, if both plain texts are English text, the XOR will show patterns related to letter frequencies and common words. This is why nonce uniqueness is not optional. It is the foundation of CTR mode security. Never reuse a nonce with the same key under any circumstances. Simple example: encrypting a message. Let's walk through a concrete example to make CTR mode crystal clear. Imagine you want to send the secret message, "Hello," to your friend. We will encrypt this message using CTR mode with AES to keep things simple for illustration. Let's say each letter is one block, though in reality AES blocks are 16 bytes. First, you need a secret key. Let's say your secret key is my secret key 123. You also need a nonce, which must be unique for this message. Let's use nonce number 42. Now, here is how the encryption works for each letter. For the letter H, which is the first block, we create a counter block by combining the nonce 42 with counter 0. So our counter block is 42-0. We take this counter block and encrypt it using AES with our secret key, my secret key 123. Let's say AES turns 42-0 into the encrypted value X7K9. This encrypted value is our keystream for the first block. Now we take the letter H and XOR it with the keystream X7K9. In simple terms, XOR is like a special mixing operation. When you XOR H with X7K9, you get a scrambled value, let's say Q2. This Q2 is the first block of our ciphertext. Notice that we never encrypted the letter H directly. We encrypted the counter block 42-0, and then mixed the result with H. For the second letter E, we increment the counter to 1. Our counter block is now 42-1. We encrypt 42-1 with AES and our secret key, getting a different keystream, let us say M3P8. We XOR the letter E with M3P8 to get the second ciphertext block, maybe Z5. We continue this process. For L we use counter block 422, for the second L we use 423, and for O we use 424. Each time, we encrypt the counter block to get a unique keystream, then XOR the plaintext letter with that keystream to get the ciphertext. Our final ciphertext might be Q2Z5R7W3N9. We send this ciphertext along with the nonce 42 to our friend. Simple example: decrypting the message. Now let's see how your friend decrypts the message. Your friend receives the ciphertext Q2Z5R7W3N9 along with the nonce 42. Your friend also has the same secret key, my secret key 123 inches that you used for encryption. Here's how decryption works, and you'll see it's exactly the same process as encryption. For the first ciphertext block Q2, your friend needs to generate the same keystream that you used. Your friend combines the nonce 42 with counter 0 to get counter block 420. Then your friend encrypts 420 using AES with the secret key, my secret key 123. This produces the exact same keystream X7K9 that you got during encryption. Now, Here's the magic of XOR. Your friend takes the ciphertext Q2 and XORs it with the keystream X7K9. Remember that during encryption, you did HXOR X7K9 equals Q2. When your friend does Q2 XOR X7K9, the XOR operation reverses itself and gives back H. This is because XOR has a special property where if you XOR something twice with the same value, you get back the original. For the second block Z5, your friend increments the counter to 1, making counter block 42-1. Encrypting 42-1 with AES produces keystream M3P8, the same keystream you generated. XORing the ciphertext Z5 with M3P8 recovers the letter E. Your friend continues this process for all 5 blocks. For block 3, counter block 42-2 produces keystream P1R6, and R7 XOR P1R6 equals L. For block 4, counter block 42-3 recovers the second L. For block 5, counter block 42-4 recovers O. Your friend has successfully decrypted the entire message back to hello. Notice that decryption used exactly the same operations as encryption. Your friend encrypted counter blocks with AES, similar to your method. Your friend XORed the result with data, just as you did. The only difference is that you XORed plaintext with the keystream to get ciphertext, while your friend XORed ciphertext with the keystream to get plaintext. It's the same process, but with different input. Understanding XOR in detail. Let's take a moment to deeply understand the XOR operation because it's at the heart of CTR mode. XOR stands for exclusive OR, and it's a binary operation that works on bits. Understanding how XOR works will make everything about CTR mode crystal clear. XOR follows simple rules. If 2 bits are the same, XOR gives you 0. If 2 bits are different, XOR gives you 1. So, 0 XOR 0 equals 0, because both bits are the same. And 1 XOR 1 equals 0, also because both bits are the same. But 0 XOR 1 equals 1, because the bits are different. And 1 XOR 0 also equals 1, because these bits are also different. Let's see a simple example with actual bits. Suppose you have the letter A in binary, which is 01000001, and you have a keystream byte 10110101. When you XOR them bit by bit, the first bit is 0 XOR 1 which equals 1. The second bit is 1 XOR 0 which equals 1. The third bit is 0 XOR 1 which equals 1. Continue this for all 8 bits, and you get the ciphertext byte 11110100. Now here's the magical reversible property. If you take that ciphertext byte 11110100 and XOR it with the same keystream byte 10110101, what happens? First bit, 1 XOR 1 equals 0. Second bit, 1 XOR 0 equals 1. Third bit, 1 XOR 1 equals 0. When you complete all 8 bits, you get back 01000001, which is the original letter A. The XOR operation undid itself. This is why CTR mode encryption and decryption are the same operation. When you encrypt, you do plaintext XOR keystream equals ciphertext. When you decrypt, you do ciphertext XOR keystream equals plaintext. The XOR operation reverses itself, so the same process works both ways. Another important property is that XOR is fast. Modern CPUs can XOR multiple bytes simultaneously in a single instruction. This is much faster than complex mathematical operations, which is another reason CTR mode is so efficient. The heavy lifting is done by AES encrypting the counter blocks, and then the XOR step is extremely quick. Complete encryption flow with real data. Let's walk through a complete encryption example using actual byte values, so you can see exactly what happens at each step. We'll encrypt the word cat, which is 3 letters, meaning it will form 3 blocks. First, set up Our secret key is a 128-bit AES key. Let's represent it as secret key. Our nonce for this message is 100. We'll start our counter at 0. Now, let's encrypt each letter. For the first letter C, the ASCII value is 67 in decimal, which is beginning with 01 ending with 11 in binary. We construct counter block 1 by combining nonce 100 with counter 0. Let's say this gives us the 128-bit value represented as 100 padding. We feed this counter block and our key into AES encryption. AES is a complex algorithm with multiple rounds of substitution and permutation, but for our example, let's say it outputs the encrypted counter as the byte beginning with 10 ending with 11. This is our keystream byte for block 1. Now we XOR the plaintext C, which is beginning with 01 ending with 11, with the keystream beginning with 10 ending with 11. Going bit by bit. 0 XOR 1 equals 1, then 1 XOR 0 equals 1, then 0 XOR 1 equals 1, and so on. The result is beginning with 11 ending with 00. This is our first ciphertext byte. For the second letter A, its ASCII value is 65 in decimal, which is beginning with 01 ending with 01 in binary. We increment our counter to 1. So, our counter block is now 101 padding. We encrypt this with AES and our key. Let's say AES outputs beginning with 11 ending with 00 as the key stream. We XOR plaintext A, which is beginning with 01 ending with 01, with key stream beginning with 11 ending with 00 to get ciphertext beginning with 10 ending with 01. For the third letter T, its ASCII value is 84, which, in binary, is beginning with 01, ending with 00. The counter increments to 2, giving us the counter block 102 padding. AES encryption produces a keystream byte. For example, beginning with 10, ending with 11. We XOR plaintext T, which is beginning with 01, ending with 00, with this keystream, beginning with 10, ending with 11. This results in the ciphertext, beginning with 11, ending with 11. Our final ciphertext is 3 bytes, beginning with 11 ending with 00, beginning with 10 ending with 01, beginning with 11 ending with 11. We send this ciphertext along with the nonce value 100. The receiver can use nonce 100 with the same key to decrypt and recover CAT. Complete decryption flow with real data. Now let's decrypt the ciphertext we created to recover the word CAT. The receiver has the ciphertext bytes beginning with 11 ending with 00, beginning with 10 ending with 01, beginning with 11 ending with 11, and the nonce value 100. The receiver also has the same secret key. Let's decrypt each byte. For the first ciphertext byte, the receiver constructs counter block 1 using nonce 100 and counter 0. This gives the same counter block 1000 padding that was used during encryption. The receiver encrypts this counter block using AES with the key, and because it is the exact same counter block and key, AES produces the exact same keystream byte. Now the receiver XORs the ciphertext byte beginning with 11 and ending with 00 with the keystream byte beginning with 10 and ending with 11. Let's do the XOR bit by bit. For the first bit, 1 XOR 1 equals 0. For the second bit, 1 XOR 0 equals 1. For the third bit, 1 XOR 1 equals 0. For the fourth bit, 0 XOR 0 equals 0. For the fifth bit, 1 XOR 1 equals 0. For the sixth bit, 1 XOR 1 equals 0. For the seventh bit, 0 XOR 1 equals 1. And for the eighth bit, 0 XOR 1 equals 1. The result is beginning with 01 and ending with 11, which is ASCII 67, the letter C perfect. For the second ciphertext byte beginning with 10 ending with 01, the receiver increments the counter to 1, making counter block 101 padding. AES encryption of this counter block produces keystream beginning with 11 ending with 00, matching the encryption process. The receiver XORs ciphertext beginning with 10 ending with 01 with keystream beginning with 11 ending with 00. Bit by bit. 1 XOR 1 equals 0. 0 XOR 1 equals 1. 0 XOR 0 equals 0. 0 XOR 0 equals 0. 1 XOR 1 equals 0. 1 XOR 1 equals 0. 0 XOR 0 equals 0. 1 XOR 0 equals 1. The result is beginning with 01 ending with 01, which is ASCII 65, the letter A. For the third ciphertext byte, beginning with 11 and ending with 11, the counter increments to 2, giving a counter block 102 padding. AES produces a keystream beginning with 10 and ending with 11. The XOR operation. Ciphertext beginning with 11 and ending with 11 XOR keystream beginning with 10 and ending with 11 equals beginning with 01 and ending with 00, which is ASCII 84, the letter T. The receiver has successfully decrypted all 3 bytes and recovered the original message cat. Notice that every step of decryption was identical to encryption. Construct counter blocks, encrypt them with AES, X or with data. The only difference was that during encryption we XORed plaintext with keystream, and during decryption we XORed ciphertext with keystream. The reversible nature of XOR makes this work perfectly. Why CTR mode works so well. Now that we have seen CTR mode in action with concrete examples, let us understand why this design is so effective. The fundamental insight of CTR mode is that instead of encrypting your actual data, you encrypt predictable counter values and then mix the encrypted result with your data. This simple change unlocks several powerful properties. First, because counter values are just numbers that you can generate independently, you don't have to wait for one block to finish before starting the next. If you want to encrypt blocks 1 through 100, you can immediately create all 100 counter blocks and encrypt them all simultaneously if you have multiple CPU cores. This parallelization means CTR mode can be extremely fast on modern hardware. Second, using XOR for the final mixing step is brilliant. XOR is one of the fastest operations a computer can perform, often completing in a single CPU cycle. And because XOR reverses itself, encryption and decryption become the same operation. You do not need to implement AES decryption at all, only AES encryption. This simplifies both software and hardware implementations. Third, the counter structure with a unique nonce per message ensures that even if you encrypt the same data multiple times, you get different ciphertexts. The nonce makes each encryption unique, and the incrementing counter makes each block within a message unique. This prevents patterns from appearing in the ciphertext that could leak information about the plaintext. Fourth, because each block's keystream is generated independently from a counter value, you can decrypt any block without needing the previous blocks. Want to read a byte deep within an encrypted file? Just calculate which block that is, construct the counter for that block, encrypt it to get the keystream, and decrypt just that block. This random access property makes CTR mode ideal for databases and file systems. Fifth, there's no padding needed. Traditional block cipher modes require your data to be a perfect multiple of the block size, so you have to add padding bytes. CTR mode generates a stream of keystream bytes, and you just use exactly how many you need. If you need 17 bytes, you use 17 bytes of keystream and discard the rest. Your ciphertext is exactly the same length as your plaintext. Practical implementation details. Let's talk about the practical aspects of implementing CTR mode correctly. When you're building a system that uses CTR mode, There are several important details you need to get right to ensure both security and proper functionality. The first critical detail is nonce management. You must have a reliable system to ensure every nonce is unique. If you are using sequential nonces, you need persistent storage. When your application encrypts a message with nonce 42, you must save that you have used nonce 42, so the next message uses nonce 43. This state must survive application restarts and crashes. Many systems store the last used nonce in a database or configuration file. If you're using random nonces, you need a cryptographically secure random number generator. The standard library random functions in most programming languages are not cryptographically secure. They're designed for simulations and games, not security. You must use your operating system's cryptographic random generator. In Linux, this is dev urandom. In Windows, it's crypt-gen random. In Python, use the secrets module. In Java, use secure random. These generators are designed to produce unpredictable random numbers suitable for cryptographic use. The second detail is counter construction. You need to correctly combine the nonce and counter into a 128-bit block. The typical approach is to use the first 96 bits for the nonce and the last 32 bits for the counter. But you must pay attention to byte ordering. Is your counter Big Endian or Little Endian? Most cryptographic standards use Big Endian, where the most significant byte comes first. Make sure your encryption and decryption use the same byte ordering. The third detail is handling the nonce in your protocol. The nonce is not secret, so you can send it in the clear along with the ciphertext. A common approach is to prepend the nonce to the ciphertext. If your nonce is 12 bytes, the first 12 bytes of what you transmit are the nonce, and the remaining bytes are the ciphertext. The receiver reads the first 12 bytes to get the nonce, then decrypts the rest. The fourth detail is counter size and limits. A 32-bit counter gives you 2 to the power of 32 blocks, which is about 68 billion blocks. With 16-byte AES blocks, that's about 64 gigabytes. If you need to encrypt more than 64 gigabytes with a single nonce, you need a larger counter. Some implementations use 64-bit counters, but the nonce and counter together must still fit in 128 bits, so a 64-bit counter means a 64-bit nonce. The fifth detail is authentication. CTR mode only provides confidentiality, not authentication. An attacker who flips bits in the ciphertext will cause corresponding bits to flip in the plaintext when decrypted. For real-world applications, you almost always need to add authentication. You can use AMAC like HMACSHA-256, computing it over the ciphertext and nonce. Or you can use an authenticated encryption mode like GCM, which combines CTR mode with built-in authentication. Conclusion and summary. We have completed our comprehensive walkthrough of AES CTR mode. Let us recap the key points. CTR mode transforms a block cipher into a stream cipher by encrypting counter values rather than plaintext. The encrypted counters form a keystream that is XOR'd with the plaintext to produce ciphertext. The counter block is constructed by combining a unique nonce with an incrementing counter value. This ensures that each block uses a different keystream, preventing patterns in the ciphertext. The absolute requirement is that you must never reuse a nonce with the same key, as this completely breaks the security. CTR mode has exceptional properties. These include supporting full parallelization for both encryption and decryption. It also provides random access to any part of the ciphertext. Furthermore, it does not require padding. And finally, it uses only the encryption direction of AES even for decryption. These properties make it ideal for high-performance applications. When implementing CTR mode, you must pay careful attention to nonce generation and tracking, counter construction and wraparound, integration of authentication, and protection against side-channel attacks. Following security best practices is essential to maintaining the security guarantees that CTR mode provides. CTR mode is widely used in real-world systems, including TLS, IPsec, disk encryption, databases, and cloud storage. Its combination of security, performance, and practical features has made it one of the most popular modes of operation for AES. Thank you for your attendance. Please consider subscribing to the channel.